Okay, so now we're going to look at dye substitution, and in the dye substitution we'll have something like this. Okay, so we'll have two methyl groups on a cyclohexane. So you have the cis, which are the two methyl groups in the same direction. You can draw them like this with the wedges, or like this going in the same direction. And then we'll look also at the trans, okay, where one group is going to the front, one is to the back, or you can draw it like this. Just remember, in cyclic compounds, you can have the cis and trans because of the lack of rotation of rings, right? So if you have a straight chain, as we talked about before, in straight chains, you can, rotate, and so there is no cis and trans as such. But in cyclic compounds, you can't rotate. So the groups are stuck, okay, where they are. So that's why we do the cis and trans. Okay, so what I'm going to do here for us is I'm going to go ahead and use a clean ring, just a skeleton. I don't want to use this because there's just too many hydrogens on this, okay? And so it's hard to focus on the methyl groups. You know, you already understand the nature of the steric hindrance with the hydrogens, and the axial. So it's much better to see the ring just with where the methyl groups are, okay? So once you understand how that's working. So here is going to be the ring. Now remember here, when we look at any kind of a ring structure or any kind of bonding, we have the ball and stick model. And the ball and stick model is kind of like this, where you have the ball here and then the stick, right? The stick is actually the bond, but in general, the bonding is overlaps of orbitals, as we've said before. So, you don't really see the stick, right? Those are called the space-filled models, okay? And the space-filled models visually are not that great for us sometimes because our vision is not as deep, okay, for us to understand all those things. So that's why we have this, and that's how I'm showing you the flips. And the reason I'm saying all of this is just for you to understand that in reality, these sticks are not there, okay? So just for you to understand. Anyhow, okay, so here is the chair, and remember we do the flip, right? So we get the other chair. Now for the two methyl groups, okay? So I'm going to go ahead and take the cis first, okay? This one, where you have the methyl groups on the same side. So what does it mean that groups are on the same side? We call it cis, but spatially they're supposed to be on the same side. So which means that if I have something like this and I have to place my methyl group here, the other methyl group should be on the same side as this, which if this is going up, my other methyl group should also be going up. Okay, now see, this is axial, this is equatorial. So if you have cis, it doesn't mean both groups are going to be equatorial or axial, okay? They have to be going in the same direction, which is up or down. You can have it down also, okay? But remember what I told you before is that whenever you start drawing structures, you should always have the first one going up, okay? And then start from there. It's a good point to start with, okay? Always, it's a nice reference point. So here, if this is going up, this axial group is going up, the equatorial is now going up, not the axial. The axial will be going down, okay? It's always up, down, up, down, up, down. That's what I do when I draw my ring structures, okay? Just to give you an idea how I do when I do this. And you know what? I talk to myself all the time. So here is, our ring, okay? So this is what I do. Up, down, up, down, up, down. Okay, so this is how I do it. And then if this is going up, this has to be going down. Okay, this is going down, this is going up. So this is kind of how I go through my life with cyclohexane. Okay, and so you can use that for the models also like this. So if this is going up, this is going up as well, okay, because the next axial will be going down. Okay, so this is all fine. Now I have to do the flip, right? Because you can have two conformations, and usually the questions will be like, okay, draw the conformation out, which one is the more stable one, okay? So here if we do the flip, remember this is axial, this is equatorial. So if we do the flip, this goes up, this goes down. So now what do we have? We still have an axial going up and the equatorial going up. What happened? in this case, really nothing much happened. Why? Because the group, one group is still axial and the other one is still equatorial. They're both going up, but still one is still axial, one is still equatorial. So if both of them are one axial, one equatorial, well, then both the structures are technically equal. Okay, that's what we would say in energy. All right, so now what we're going to do is we're going to look at the other one, okay, which is the trans. So in the trans, one is going up, one is going down. So I'm going to go ahead and leave my axial right there and see how I actually literally have to break the bond in order to make the trans. And that is how I know that this is a geometric isomer and not a conformer. Because in a conformer, you just have to rotate things around. Okay, so now I have a trans. Okay, so in the trans, what do I have? One group going up, the other one going down, because they're supposed to be in opposite sides. Okay, so that is my trans conformer, actually trans structure isomer. Okay, so that's what I'm doing. All right, now the flip. So once I flip this, the axials, yeah, you know it already, right? The axials will become the equatorials. So here we go. So let's just see it in action, and then here are the two equatorials. Okay, and so this one equatorial going down, this one equatorial going up, and it's kind of hard to see it. There you go. Okay, and that's where the dihedral angle comes into play. Here, let me put it this way so you can see that one of them is going down and the other one is going a little bit up here. Okay, there you go, down and up. So going in opposite directions, right? Up, down, that's how it's supposed to be, because this is a trans relationship. So again, if I do the flip here, these two become axials. Flip, and they become equatorial. So remember our rule for what the stability should be. Bigger groups should be in equatorial positions to be stable. So in this kind of an isomer, in the trans isomer, we can say that the trans isomer is going to prefer this conformation in which both the groups are equatorials. Okay, and so when we have our answer, in this case, remember, this one group was axial, one was equatorial, and even if you switch their amount, this became equatorial, this became axial. But in this case, you know, when you have these two groups, there you started with axial and axial, and now you have equatorial and equatorial. So this is going to be more stable. These two are exactly the same kind of structure, so no difference, okay, in there. So here, this conformation where you have the two equatorials is going to be more stable. So trans is more stable because of that also, okay, because the conformation is preferred to be equatorial in trans. So what are these things? Why are we studying this kind of a thing? We have to understand how molecules actually exist in nature, how they're formed. Do we want to form something like this? Yes, because it's more stable, right? When you have molecules that occur in nature, they will prefer to be like this, okay? They will not prefer the axial state. They will prefer the equatorial states. Similarly, when we do synthesis, when we transform one molecule to another, they will prefer certain conformations. Okay, so right now, remember, this is the basics. Okay, all of this we have to apply when we get to synthesis. So anyhow, this is the dye substitutions.